we are doing at Professor Scully's lab. It's about studying and designing new corrosion-resistant alloys out of multi-component principal element alloys, which are high entropy alloys, which has a lot of principal elements in them, which can be designed both computationally as well as experimentally to form, to make them behave or perform in your own ways, or depending upon the applications you want. So, our aim in the project is to design such an alloy for really good corrosion resistance, and also study how they behave in certain atmospheric conditions like marine environment or in space applications. So, what we do in the lab is we the people in the project, they design computationally using different models to make us experimentalists know what sort of elements we can add in one alloy to make them single phase, because our aim is to make them FCC single phase, as well as really good passivating elements in the alloys. So they tell us what to add, and we make them, and we get them in form of some coupons. And here we test those coupons or alloys using electrochemical cell. First we begin with the DC type of testing, where we just use the alloy and expose it to a solution under pure nitrogen gas environment to make it deoxidized or de-aerated. And then we apply a potential from certain range, and within a certain range, to obtain a form of current. So what we are doing here is we are applying a potential at, let's say, negative 1.3 volts, and we are observing the current within that at that potential for a long period of time. So in this way, we are actually reducing the air-formed oxide, which was formed on the coupon just by exposing it in the air. And then after reducing it, we will oxidize it so that we will study the oxide formed within the solution on that alloy, and how is it behaving within the solution, as well as how thick or dense or defect-free is the oxide. That's our aim.
Thanks, Deb. So now I'm going to take you to the second step of a lot of our HDA analysis, and that's XPS. Very thankful for the MMCF to be able to use their equipment, as you see here on the right. So we're going to pump it down to a vacuum and use X-ray signaling to be able to tell not only what elements are within the passive film, but how they are bonded. Are they bonded in the oxide, a hydroxide, even a multi-element smell? And this is important because when you have 7 or 8 different potential metals that could be the cause of your passivation, it's important to look at which ones are actually forming those protected species and in what fractions, so we can really take a marginal effect of each element and further use those steps in alloy design. So if you look here on the screen, in a given spot, you can actually take spectrum for many different elements and then compare the respective intensities for those elements as well as those of the species. Thank you for your time. Feel free to email Deb and/or myself with any questions about the project. As mentioned, there is a similar project being open for future grad students. So it's a great experience, a lot of good material to be focusing in on and for the future research in. Thank you for your time.